So I got another question about section 1.9, graphing transformations of the plane. I gave you previous video talked about rotating transformations that rotate about some angle. But another question came in about, can we visualize what it looks like when we're looking at a transformation that reflects all the points in the plane about some line y equal to mx. Okay, so we're gonna, and where m, is the slope of that line, let's say that's a over b. You'll notice that that's the case. Remember m, the slope is rise over run. So in other words, if we went up some distance a, we would be going across some distance b, right? So for example, this point here would be b, comma a. Now this actually still holds, of course, if a or b was negative. The picture would look different, but the same statements hold. Also, we need to examine this angle. Let's call that alpha, that the line makes with the positive x-axis. Okay, hold on a second. Yeah, that helps. Okay, so alpha here is equal to the arctangent, right, of, well, that height is a, that height is b, so it's the inverse tangent of a over b. Okay, so for any one of these lines, it's got some angle alpha associated with it. To figure out what its standard matrix looks like, we just have to ask ourselves, what does it do to E1, what does it do to E2, right? Put those in a matrix. Well, let's see. So a good way of thinking about this is looking on the unit circle. Mind you, the unit circle has angles, has these vectors E1 and E2 right on it, right? And if you reflect them about one of these lines, y equal to mx, which would be dividing that circle into two parts, their images would also be on the unit circle. Try that picture again. So, for example, all right, so let's see. So here is unit circle. Here is E1 sitting right here. Okay, and let's say that the line that we're talking about, L, goes through this. Oh dear. Yeah, let's say that's L. Okay. So if we reflect E1 across that, you'll notice when it does that, it has to go through that angle alpha. There's that angle alpha. And its image is, if that's reflection across, that image is going to be exactly alpha away from that line L, right? So if you find the coordinates of this point, then we know exactly what to put in for the components of T of E1. Well, that's actually kind of simple. We drop a perpendicular down here, right? That angle that it makes with the positive x-axis is 2 alpha. So what does T of E1 look like? Its x-coordinate is the cosine of twice alpha, and y-coordinate is sine of twice alpha. Okay, so for E1, that's pretty straightforward. For E2, slightly more complicated, but not impossible. Okay, so for E2, we draw a unit circle. We find E2 inside there. That will look like this. Here's E2. Right, there's E2. If I put that same line L at that angle alpha for the positive x-axis in there, there's L, there's this alpha. Slightly more intricate reasoning here. If that's alpha, then this angle here is pi over 2 minus alpha. It's complement, right? Okay, so if we're going to reflect, sorry, notation's gone a little bit haywire there. If we're going to reflect E2, the vector, about this line, it has to go through that angle pi over 2 minus alpha. Well, what's that new angle going to be called? That angle has to be pi over 2 minus alpha more in this direction. Notice that's the same thing as going alpha in the positive direction and then minus that pi over 2 minus alpha. Subtracting a positive angle, remember that sends you in the clockwise direction. So the algebra simply is that alpha minus pi over 2 plus alpha is the same thing as that, and that's equal to 2 alpha minus pi over 2. So what that ends up looking like is something like this. Okay, so this is going to be T of E2 there. Again, how did I get to it? If I think of from the line alpha, L, I was forced to go alpha this direction and then minus a pi over 2 minus alpha in the other way, and I end up right here. Well, so its angle is this one, and therefore coordinates of that point, and therefore of this vector, are, so T of E2 will look like cosine of 2 twice alpha minus pi over 2 sine of twice alpha minus pi over 2. Okay, so that's in general. Now, I should point out that on my quizzes and tests in this class, I generally keep the angles alpha of these lines one of the special angles. So you're really only going to be seeing, in our class, you really don't only be seeing alpha equal to, say, pi over 6, which is 30 degrees, or pi over 4, which is 45, or pi over 3 equal to 60 degrees, or their opposites, plus or minus, plus or minus, plus or minus. So you don't have to memorize this formula in general, but I can show you an example where if we choose one of these types of angles, there's all sorts of nice, well-known angles to play with, we end up getting the same sort of thing. Oh yeah, I should write up here what this gives us in general. Right? If T is this transformation that's reflecting about the line y equal to mx, Then a sub t is going to be t of e1, which is cosine twice alpha, sine twice alpha, and cosine twice alpha minus pi over 2, sine twice alpha minus pi over 2. That's true in general, right? Or any line L that's at an angle alpha. Let's look at a typical type of example of one of my test or quiz questions using one of these nice angles. All right. So that's, we'll check back with that general theory in a second. Let's do an example. Okay, so let's say that alpha is pi over 6. So suppose alpha, suppose alpha is equal to pi over 6. What do we have then? I'm not going to use the formula, I'm just going to duke it out. We're going to see it agrees with that formula. So you don't want to memorize that. I'm just showing you that it's possible in general to do it. If that's 30 degrees or pi over 6, right? So if that's 30 degrees, then its image, t of e1, here is going to be another 30 degrees up, in other words 60 degrees. So what's t of e1? T of e1 will be equal to, let's say 30, 60, 90, so that'll be 1/2 square root of 3 over 2. Okay, what's happening with e2? So here's e2. If you reflect it across that line L, again, this is the line associated with 30 degrees to the positive x-axis. So that's 30 degrees there. Then this complement here is, complement is 60 degrees. So if you're reflecting E2 across that, well, then its image is going to be another 30 degrees down here, isn't it? So T of E2 will be down here. So that was 60 degrees to the line L. We got to go another 60 degrees, reflecting away from it. There's another 30 degrees there. Oh, what did the coordinates of that point? At the head, gives us the coordinates of the vector, square root of 3 over 2, negative 1/2. So if we put that together, we end up getting, we end up getting that T associated with this 30-degree reflection is equal to T of E1, 1/2 square root of 3 over 2, T of E2, square root of 3 over 2, negative 1/2. So for comparison purposes, we wonder, is that the same as this formula in general would have given us? In other words, this is for alpha. What would this formula say A of T sub 30 degrees is? Or pi over 6, right? So that would look like, I hope you guys can see that. Yeah, that'll look like the cosine of twice alpha, which is 60 degrees, sine of 60 This would be the cosine of 60 minus pi over, so 60 minus pi over 2 is 90. So that's minus 30 degrees, sine of minus 30 degrees. And sure enough, as you can see, these numbers are looking very familiar to the angles we were dealing with. That is exactly what we have here. So again, I will only be giving you problems where the angles alpha in question are these nice ones here, plus or minus these, right? So the lines could be not positively sloped, but negatively sloped. Still, the angles will be nice, okay, for the purposes of reflecting. All right.